Good morning, everyone. My name is Werner Brand. I work at EGENES and SRUC. We do the routine genetic and genomic evaluations. And in our extra time that we find ourselves to have, we have sort of done a bit of research in deep learning. And we wanted to share some of the research we've done and also maybe dream about where we can fit this into agriculture and especially in the livestock industry. So I guess where to start would be as to what is deep learning. Not a lot of people know what it is exactly. But in a very broad sense, it's algorithms or programs that seem to learn. They learn by themselves, and they do this by the analysis of huge amounts of data. So the idea is to simulate the animal brain. And just on a side note, this forms part of a broader term of machine learning, which is a set of algorithms and programs that can analyze data on its own without you implicitly telling it what to do with that data or necessarily telling it what that data is. But I think it's best answered as we look as to why we would use deep learning. So in a nutshell, why would we use deep learning? And the reason is we need to solve complex problems. Problems that are more complex than we have the ability to solve ourselves. And to illustrate this, we can look at a set of digits. These are obviously printed. They are font, so whether they are bigger or smaller, they have the exact same shape. So the shape of this digit is its feature. A 4 is a 4 and a 5 is a 5. And you could, if you put these digits in an image, you could relatively easily write a program to look at an image and identify a 1 or 2 or 3 and a 4. But when you add handwritten digits, it becomes slightly more complex. And even when you add in more people's handwriting, it becomes ever so more complex because people write differently. And now it would be very difficult to understand, how to identify these digits and images. And that's where deep learning comes in. So if we look at the number 4, if we only had the printed font, the feature would be the number 4. It has a very specific shape. But if we look at the first handwritten digit below it, it's obviously slightly different shape. So we need something else to do this. And this is, I think, what answers what deep learning is really. It's a progressively extracting higher level features from the original features. So before we had the numbers on its own, we're now looking for these higher level features. And what are they? So the computer program would have a look at this data and see something that these 4s have in common is the smaller cross-like shape. And so that is a higher level feature that it found. And it seems to be available in all the 4s it sees. So the computer makes an assumption and says, well, this is clearly the identification for a 4. And it goes and looks at all of the data again and validates and see if this holds true. And when it does it, it would see, well, it doesn't get confused with any other numbers, but in some cases you get a slightly skewed cross in an 8, but you also get it in a 7 there. So progressively, the computer says it's a good feature, but it's not the only feature in that number. And I'll have to find something else. And it finds a right angle. And then it figures out, well, that is the feature for the number 4. If I find a right angle and a cross shape, that really doesn't get confused with any other numbers. And that is how deep learning works, essentially, in a very broad sense. So if you look at the number 9, the computer might find this shape over there and say, I can write an exponential equation. That seems to be common in all 9s, but it gets confused a lot. It doesn't get confused with 3s or 4s, so it's a good enough feature, but it needs some more. It adds another shape in there, and it says, well, this is a good identification of the number 9. But you'll see there clearly in some cases, a number 2 has that same features, and that's something we all should be realizing about deep learning and machine learning. It's a very useful tool, but it can make mistakes. And it's not 100%. If anybody claims that deep learning models are 100%, they probably didn't need deep learning at all, and it was a bit of an overkill. So General applications of deep learning, you may or may not know that you're already using it. It's everywhere. It's heavily invested in by large companies like Google, Facebook, Microsoft, Apple. So the first most common one when people think about machine learning and artificial intelligence would be self-driving cars, models that can determine what is in its surroundings. Is there something in its way, and if it's something, should I stop for it? If it's just a leaf blowing, the car shouldn't come to a stop. It should move on. If it's a human, it should most probably stop. In healthcare, the application is vast. It's being used everywhere to analyze tests, medical images for cancer detection, and deep learning is doing really well in that sector. And it offers a low-cost answer to a big problem. It speeds up time, but it's consistent and it's reliable. Voice-activated assistants going from Siri, Cortana, OK Google, Alexa, we all use it, or most of us use it. And it's not just a fancy tool, it's really a personalized assistant that you can use to schedule meetings, to wake you up in the morning, to remind you of things, to look up answers. Handwritten recognition, as I explained earlier, lots of valuable documentation is still in handwriting. Instead of employing people to read through them and retype them, handwritten recognition can be used to just scan documents written by humans and type them over into documents. Image recognition, the same as self-driving cars, to detect objects in an image. What is it? Is it a car? Is it a bicycle? Is it a person? And even more importantly, if it's a person, can it ID that person? It's used in police investigations to try and find criminals. We've experienced it when we went to Silicon Valley at the airport in Los Angeles. We would go into the airport, check in, and from there, it's all facial recognition. You don't need a passport anymore. You don't need a ticket by your hand. You just walk around. Your face is constantly scanned, and they know exactly who you are. Advertising, most of you might already know about that. Personalized advertising, targeted advertising, but even on social media, it affects elections. It's used literally everywhere. And also it's used to predict natural disasters, where vast amounts of information is digested to predict whether volcanoes will erupt, earthquakes will occur, storms or tsunamis will occur. So, important people in deep learning. These are the 10 most important people in deep learning. I hope you don't recognize any of them, because it's a bit of a lie. I want to talk about data generation, and these faces were found on a website called thispersondoesnotexist.com. They come from deep learning, deep neural networks that have been trained on so many faces that they can dream up new people. And if you go on that website, it's fascinating. I mean, you as a human cannot tell the difference whether this is fake or this is real, and none of these people exist. They might resemble someone you know, but they don't exist at all. And I know all of you are thinking, why would I show you this? This is mildly interesting, but I'm just trying to buy time because I don't have a lot to talk about. You would be wrong. I can talk a long time, but also this has some practical application. So a common theme that occurs in data science companies is a medical practice would go to a data science company and ask them, we want to look at our medical images and detect cancer. Can you help us with that? Can you build a model that can detect cancer in medical images? And the data science company says, well, that's perfect. Give us your data and we will give you in return a model that can do this. But the medical practice then says, well, we can't do that. It's confidential information. How can we get past this? So a new technology that exists is called a generative adversarial network. And it's a long name, and it's got two descriptions in the name, but the reason for that is because it is essentially two networks. So the medical practice would take this network to their practice, and they would start training this network on their own. And the first part is the generative part, where it would look at the images and try and dream up something that looks quite similar to it. But the second network, the adversarial network, would look at it and say, well, I can clearly see this is fake. This doesn't help me. You need to retry. And that generative network would keep on changing and improving up until a certain point where the adversarial network can't tell the difference. When it reaches this point, the medical practice sends the network back to the data science company, and they can use this network to dream up all the medical images that they need to train the final model in detecting cancer in these images, and finally send that back to the medical practice. And to some extent, we've been using similar techniques in synthesizing data that we don't already have to try and train neural networks, and my colleague Scott will talk about that a bit later as well. So this already exists, and this is really powerful. So current research in MER, and I'm going to touch on briefly on what mid-infrared is, because Scott will be talking about that as well. But essentially, mid-infrared spectroscopy is the study of the rotational and vibrational structure of molecules. So you shine a light on a milk sample, and you mid-infrared light, and you measure the amount of reflectance and absorbance. And that's quite characteristic of the molecules. So it helps you to identify what type of molecules are in that data. At SRUC, we have more than 20 billion of these spectral points. You get 1,060 values per each spectral record. So for every cow that's going through routine milking, would get a spectral record back, and we would have these arbitrary 1,060 values per milk sample. And it's been used for the prediction of fatty acid content and body energy status, but we wanted to see if we can repurpose this and use it for something else. So we decided on pregnancy, and our objective was, can we predict the pregnancy status of a dairy cow from this routine milk MER? Now, it's important to note at this point that our goal is not to do a pregnancy diagnosis on a cow. Our overall goal is to rather know when a cow is pregnant and monitor that cow and make sure while she's doing routine milk recording, is she still pregnant? Is this a viable pregnancy, so you don't get to the end of the lactation, you dry off and you realize the cow is not pregnant. The tools we use for this, basically two things. It's a powerful GPU-enabled computer, and GPUs, it's just graphical processing units. It's like graphical cards that's used for computer gaming, but they have shown to be really well equipped to handle deep learning equations. And we also do a process called transfer learning. So like I showed before, when we extract those higher level features, you can take a model off the shelf that has been trained by Google or a large company on millions and millions of images, and they are well trained to extract high-level features. So you can take that model, adapt it slightly to your specific need, and then just go on from there. So you already have this pre-trained model, in a sense. So what our data looks like, this would be a typical scenario of a cow that calves. She's inseminated twice, and then later on she calves again. So we had a look and we said, well, if we find any spectral records for a cow between calving and the first insemination, she will definitely be not pregnant. And if we find any spectral records between the last insemination and a subsequent calving, she must be pregnant in that area. Any spectral records can be labeled as pregnant. But we had this difficulty in the middle here. We couldn't really use it because, you know, she was inseminated, and 30, 40 days later she was inseminated again. What was the reason that the farmer missed that insemination, or was it purely that she got pregnant but sort of rejected or resorbed the embryo? So we were stuck with those two outer limits of the lactation, essentially. So this is typically what a spectral record would look like if you make a plot of it. But to use transfer learning, we needed really images, because that's where it was trained on images. So we ended up taking those spectral records and we made our own very ugly images from it. And just by cascading the data slightly, we ended up with these grayscale images that really doesn't look like something, but already you can see there's some features in there. There's like a bright starry shape in the middle, and those straight lines beneath it. So there's already some features in there, and we wanted to know, can the model extract those features, and are they unique to a cow that's pregnant or non-pregnant? So we did the training, we used transfer learning, and we look at different metrics, how to evaluate if this model is working. One of those metrics is the number of correct predictions divided by the total number of predictions, and that would be our validation accuracy. So when you train a neural network, you essentially have two data sets, both used during training. The model would take that, train a bit on it, learn from it, and then try to predict on the validation data set. And then it would look at the answers of that validation set and see, is it right or is it wrong? And depending on how well it performs, it would iteratively go back again, make some adjustments, try to learn something new, validate again. So we look at validation accuracy because the assumption is if the validation accuracy is good, that's what you expect to see in real life, because the model didn't really use that for training, it just used it for validation. Another metric we look at is the validation loss. And that is the statistical distance between the predicted and the real value. So if a cow is pregnant and we said that label is 1 and the model predicts 0.999, the difference between the two is very low. And that's good because it's so close to the real answer. And the opposite is true. If the cow is not pregnant, it's labeled as a 0. And if it predicts 0,001, that means it's fairly accurate in predicting that right. So this value can range from infinity to 0, and you try to get it as low to 0. In a certain sense, if you look at a binary trait as well, if a model predicts a value of 0.5, if you round that up, that would become 1, and if the cow is pregnant, that model would be completely correct. But if the cow was not pregnant, the model would be completely incorrect. And that's what the accuracy tells you. But if you look at this loss function, you would see that the model really doesn't know what the cow is. It's right in the middle. So that's a very, very important metric that we use. But ultimately, we need to go and look, after we train this model, look at inference data. So it's a new data set that the model has never seen before, but we still know the answers. So we just give it the features, the spectral data. We ask it to make predictions, and we ourselves go and have a look at how well it's performing. So in the inference data set that we did here, we got an accuracy of 88%, which is fairly good. I mean, it's a good estimate. It's far beyond 50% or just a coin flip. But it is slightly worrying to us that the validation accuracy is so high, but the inference accuracy is slightly lower. So we're working on further development on this, and this is a new idea. So when we train the model, we just feed it the spectral data. There's no reference of who the cow is, what lactation she is in, what is the stage of lactation. It's just anonymous, just a single sample going in. And we wanted to know if we can add in the animal effect. How can we make sure that we add in the animal effect? You can obviously add in the ID of the cow, but then the model won't be able to predict on a new cow, so that won't work. And we also wanted to add in this granularity, where if it's binary, you end up in this situation, if the model is incorrect in predicting if the cow is pregnant, it does not mean the cow is not pregnant by default, but that's what happens when you have binary. If it's not the one, it must be the other. So we wanted to see if we can add some granularity and maybe not have a binary trait. So I'll try and explain what we did with an image, because that's sort of where we got an idea from. So this is an image of a cat. I didn't have an image of a cow at that point for some reason, so this is a cat. It's a color image, but what it really looks like, if you break it down into the 3 channels, it's got a red, blue, and green channel, and that is essentially what the cat's image looks like. And when you put them one over the other, you end up with the normal color image that we know. So why is this important? It is that you can see that all 3 images are the same cat. So it's a repeat of the same thing, but it's slightly different. And in that slight difference, you might pick up a new feature that you didn't have before. So taking this idea, for some reason, I was very excited and I shouted that I had to do the same for spectral. But we only used 2 channels. And I'll explain why those 2 channels and what they are. So if you look at this data set, we have records of spectral records of a single animal, animal 1, in 2 lactations, lactation 2 and 3, and it's chronologically ordered. So the animal is not pregnant, so she probably calved, she became pregnant, we have another spectral record where she's pregnant, and then she calved in a 3rd lactation, so she's not pregnant after that. And then we joined this data onto itself and made the slightly change in there, where you put the subsequent records next to one another. So the first record would be the first 2 records combined, and this is now not pregnant anymore, but this is a cow that went from non-pregnant to pregnant. And the next one would be a cow going from pregnant to pregnant. So what we ended up is 4 labels instead of just 2. So it's not only pregnant or non-pregnant, it's this transitional state between different states of pregnancy. We have the safety in numbers that we need at least 2 records to predict, but also we've added in the animal effect now, because it's the same animal and it's 2 records that we fold and we put them like an image, but except with the 3 channels, just the 2. But we put that together. And now we have some of these instances that was very difficult to discern before, where an animal goes from pregnant to non-pregnant, even if it's naturally by calving. So this gave us some granularity and also adding in the animal effect. So we took this data, and because it's only 2 channels now, you can't make an image. To make an image, you either need 1 channel, a grayscale image, or you need 3 channels, like we had with our cat. So we couldn't use transfer learning, but we applied the same logic, and we trained this model on about 2 million spectral records, combined records now. So this has to go through the network. They are well labeled. We know, we are confident in the quality of that data. So now we have double the size, so we have a lot more features to work through. And as I said, we have this 2-part labeling system. So now we could see the number of correct predictions of validation accuracy is 88%, which is lower than we had before, but it's a more complex problem now, because it's not, you cannot easily by chance happen to predict the right label in this case, because there's 4 to choose from. But more importantly, when we validated this, or in our inference data set, so this is data the model has never seen before, and that was 128,000 unseen records, we have the same inference accuracy. So slightly lower accuracy on a more difficult problem, but at least we know what we see in research is something we'll see in the real world when we apply it. But when we looked at the results, we also saw a few interesting things, and one of them was that cases where the model would predict an animal going from pregnant to non-pregnant, when in fact the cow was going from non-pregnant to pregnant, the exact opposite, was very low. The model was really good at not getting confused between those 2 states. And similarly, a record where the animal goes from non-pregnant to non-pregnant wasn't confused at all with going from pregnant to pregnant. So we had a look and we saw, well, if we take this model and we let it predict these 4 states, ultimately the model, the label for that animal is still either pregnant or non-pregnant. And if we collapse them back into a binary state again, so whether a cow is going from non-pregnant to pregnant or going from pregnant to pregnant, the answer is she is pregnant, and the opposite is true. And when we collapsed that, we took our accuracy up to 94%. So adding granularity, adding an animal effect into the equation makes it a lot more difficult for the model, but it also forces the model not to make obvious mistakes of just being wrong and then, or just predicting to one side and happening to be the correct side to predict on. So this is ongoing research. This is not finished, but this is something that we're focusing on this stage, but it seems to be very promising. Another application we had for deep learning is in digital images. So we wanted to know if we can predict the udder furrow in dairy goats from digital images. And the reason why we wondered if we could do it is because we had access to digital images of dairy goats, and they were really well documented and well labeled. So we used the same tools as we used before, and this was part of a research project from an honor student. So typically, the scenario would be it's a dairy goat farm where they have a carousel milking parlor, and then they have a camera that's on a fixed position, and they just take timely photos of these animals, and subsequently they would go and classify for all the other traits themselves afterwards. So we cropped these images slightly to just include the udder. You could add in more traits. It was for the purpose of the honor student, we focused on one trait. And we did two models here again. One where she built the model from scratch, and another one where we used this transfer learning. So what we saw is the number of correct predictions divided by the total number of predictions. Our validation accuracy was 99%, and our validation loss was almost 0. So the model was really good at finding this udder furrow. So Jennifer, the student, she went and she classified some new images the model hadn't seen before. She classified them by herself. So this isn't the ideal comparison because the model is learning and so is she. So we used the model to validate on her scores. So it's not a perfect one, and we gave some more leeway into the interpretation. But a cross-validation, so if you look at the middle bar at 0, the orange one, that is when she predicted a 5 and the model predicted a 5. The difference is 0, and so we did a cross-validation and tried to see there. And you can see it's sort of a normal distribution, but it's quite flat. But we did see that about 78% of the predictions was within 2 points in the cross-validation, which is reasonable for a student. Classifying the difference between a 5 and a 6 might not be that apparent. But we were concerned about those extreme ones where you get a -5 or +5. Those were clearly way out. So we did this again with the transfer learning, where we used a model that's been trained so long before on all types of images. We did it again, and now you can clearly see we're up to 94% in accuracy in predicting udder furrow just from a normal digital image. And those extremes are gone. You don't see those -5s and +5s anymore. I don't think you even see +4 anymore. Yeah. So this was some good research did by an honor student. She did really, really well with it, and we're hoping to work on this slightly more and expand this even further, because if you can do it for udder furrow, you can do it for teat placement, and you can do it for leg traits. So future applications is the pregnancy status monitoring tool. As I mentioned, it's not a replacement of normal pregnancy diagnosis. It's supposed to assist farmers, assist vets. Can we keep on monitoring these cows non-invasive? They're already doing milk recording. We can repurpose that data and just offer a monitoring tool. TB infection detection, and that is what Scott will be talking about just after me. But both of these things can improve genetic and genomic evaluations as well. We try to generate more phenotypes, and those phenotypes can feed back into our core business, which is producing genetic values and breeding values for animals. Also, the automated udder classification and udder scores. This can be expanded to dairy cows just as easily. Facial recognition of farmed animals. We spoke to a student at the University of Edinburgh who's already done this work, where you can take a photo of a cow and the model will remember that cow. And so without a tag, you can maybe walk up to a cow, take a photo, and the model can tell you who exactly that cow is. I think he even developed an app that you can download and start contributing data to sort of further enhance the capabilities of this model. But ultimately, this could lead to live tracking and monitoring of animal behavior. So if you have a mechanism for automatically identifying an animal, nothing stops you to track that animal, just as we are tracked wherever we walk. Models that know that's a human and we actually know who that human is. And this can all sort of enhance your management decisions, knowing more things about your cows without you physically having to be there. We're going to start a project soon on CT scans on sheep, segmenting them into different cuts, taking body measurements, and this is all done through deep learning. And ultimately, as I said, generate more phenotypes. And this can not only feed back into genetic evaluations, but it can also stimulate new research. If we have suddenly phenotypes that we didn't have before because it was difficult to measure, it was expensive to measure. So my conclusions is deep learning is a powerful tool. We've used it, and the technology is available right now. In fact, it was available for the past 10 years. We went to a conference in Silicon Valley from Microsoft and Google and all the big companies, and Scott and myself were the only people from the livestock industry. I think there was one other company with tractors and fancy, driving techniques and stuff, but it's been there for 10 years. It's heavily invested and it's really well funded. It's well understood to some extent, and it's implemented everywhere. And we should really, really take hold of that and see what we can do with it and what tasks that are repetitive that we can automate quite easily by using this tool. I don't know, I don't think I mentioned it before, but deep learning, as I said, we use this fancy, powerful computer, but that's just for training. When it's trained, it can run on any computer. It's just the training that's computationally intense, but the execution of this can be run from a mobile device. And as I said, this will assist farmers by automating repetitive tasks. It can give us key insights into complex problems. You'll hear Scott talking about TB, which is a complex problem, and we can maybe find more answers by using deep learning and analyzing data. And we can repurpose all data, and this is really important. The spectral data was collected for lots of other purposes, not for pregnancy and not for TB. But it's there, and if it's well recorded and it's well documented, we can actually start having a look at that old data. It's already done. Dairy farmers already take routine milk samples, and we can offer more tools back in that regard. My take-home message falls under the conclusions, but data recording is important, and I know we've said this before during the conference. Data is so important, and it's never been as important as it is now because we need lots of it. We need a lot of data to train these deep learning models. But once they're trained, you can generate so many insights into your business. And best practices for data storage is something that should be invested in. Just saving your data, not deleting it or writing it on a piece of paper, unless we get the handwritten data going, but making that sort of really valuable information, save it in an Excel format and try and use best practices while you do it. It's an easy tool to use. Excel is not a difficult program, and hopefully I'm not talking to anyone specific in here. And you all know these things, but it's so simple to have quality data, have a header column that explains what is in this file. And you always need at least two things in your data. You need an ID of an animal, but you also need a date or timestamp. Without that date, if you think about pedigree recording, if you have an animal but you don't have a birthday, there's not much you can do with that animal. You don't know the age, you don't know who's the contemporaries, there's not a lot you can do with that animal. So date recording is very important along with your IDs. Date formats, this might be a little specific, but working with vast amounts of data, one of the things we always hit our head against is the format of dates. If a date is 01, 02, 03, what year, what month, and what day is that? We don't know. And what happens is we need to reject that, because you can't train these models on, sketchy data. You will get weird answers in the end. So you need to be sure of high quality data, and just sticking to a good format, and maybe year, month, day format, so you can sort this easily. If you sort it by, if your dates are recorded with the day of the month first, you can't really sort that chronologically. And also any comments that you have, maybe this might be worth noting as well, is like use keywords. Start the sentence with sick, so that, two different animals are sick with two different things, but at least we know this is a comment for sick. And that would help us and help yourselves and help anybody who's working into data analysis to easily digest data, because that is the core of all of this business. So yeah, I would just like to acknowledge everybody who's involved, give us data, give us assistance. We really do appreciate it, and that's the source of our resources, essentially, for what we do. And yeah, thank you. You can send us an email or find us on Twitter. Yeah, thank you for your time.